So, so I would like to take you through machine learning. First of all, uh, this is our course outline that I'll be going through. So I'll be providing an overview for the session that we'll be doing. For this case, we are having our first session, and I would like to begin with introduction to machine learning, because before you go deeper, you must understand what it all entails. So in our introduction, we'll go through understanding machine learning, that is definitions, and maybe later on applications. We shall look on different types of machine learning algorithms. And then we shall have a project where we will be going to have a hands-on project here. So in this case, we'll be setting up our ML environment. For this case, I hope you guys are maybe familiar with the Google Colab, Jupyter Notebook, Cargo, or DeepNote. These are environments that provide you with resources that you can use to train and run machine learning models without consuming more memory on your local machine. I hope up to that point we are at the same note. Yes, we have you can be giving maybe responses. All right, so I'm going to spend some few minutes on overview of the machine learning so that we understand some concepts on it. So I would like to go to introduction to machine learning itself. So what is machine learning in the first place? So Author Samuel, a pioneer in that field of artificial intelligence and computer gaming, coined the term machine learning, where he defined it as a field that grants computers the capability to learn autonomously devoid of explicit programming. So how can we define it in our own words? So you can say machine learning is a branch or a subset of artificial intelligence that develops algorithms by learning the hidden patterns of the data set used to make predictions on a new similar data type without being explicitly programmed for each task. So that is what basically machine learning is all about. So it's a subset, as we have said, that will be trained on a data set and then be used to make predictions on a new unseen data set. Now, this is the diagrammatical view of machine learning. So the first circle here, it's on artificial intelligence. And inside it, there are subsets, where one of it is machine learning, and the other one is deep learning. So from where you can see, artificial intelligence is a combination of machine learning, deep learning, and the intersection of data science in this case. So in machine learning, there are steps that are followed for you to be able to come up with an algorithm that can be deployed in production. So the following are the steps. Maybe some of us maybe have a better diagram to illustrate this, but this is it. So the first thing, whenever you're given a question or a project that you are needed to come up with an algorithm or a model, the first thing is to first of all understand the business question. What is the problem that you are trying to come up with a solution, or that you are trying to develop a model to solve that problem? Then you identify what are the desired outcomes. Then from there, maybe if you don't have already collected data sets, there are different ways we do collect our data sets using APIs or web scraping. Then now after we have our data, we do preliminary checks or initial steps. In this case, they are data cleaning and pre-processing. In this stage, it's where you undo missing values, you check on outliers, and then you check if there are data inconsistency. Then the next stage is where you go to exploratory data analysis. In this case, we call it EDA, where in this case, you are going to find patterns and hidden insights from the data set that you have been provided. Here, you are going to see if the data meets the statistical assumptions that have to be met. You'll see maybe if there are any issues of multicollinearity, if the data are the variables linearly separable in that case. Then the next one you'll go to feature engineering and selection. In this case, you're going to transform the existing features either by selecting, modifying, or creating new features to come up with a model that has better prediction. Then after now you are set with your variables, you go to the next stage. The next stage is model. Remember, your variables are going to guide you in what model you are going to use. Is it supervised model, unsupervised, reinforced, or semi-supervised? Then after you have identified your model, you go now to train it. In this case, you are going to split your data, then come up with the model. Then you evaluate your model to assess its accuracy. Remember, here you're trying to come up with a model that almost approximates the actual function. Then when your model is ready, you deploy it into production. And then you will be doing some checks to make sure it is in better condition, that is through monitoring and maintenance. Now up to that stage on the diagram, any question? Or you're good with it? All right. Now we go to the next one. We continue. So now, how do machine learning algorithms work? Instead, I'll take some few minutes so that I can elaborate this, so that when we begin the modeling process, you'll have an idea of what is happening. Now, how do machine learning algorithms work? So machine learning operates through a series of iterative steps, beginning with the forward pass. In this case, the forward pass is where you input the data and it is fed into the algorithm that we have chosen. Then it's used to make predictions or give outputs. During this phase, the algorithms applies mathematical operations. Please take note of this. Machine learning it's almost like pure mathematics. There is a lot of math involved behind machine learning algorithms. So the algorithm will apply mathematical operations to the input data. Then it will generate the initial predictions based on its current parameters. Following the forward pass, the algorithm evaluates the accuracy of its predictions. Now, after making predictions, it's going to evaluate its predictions using loss functions. So take note of this also, because we will also be making it to evaluate our models, which measures the disparity between the predicted outputs and the actual function. This loss function serves as a guidepost for the algorithm to understand where it is making mistakes and where adjustments are needed to improve its performance. So in this case, if you find the loss is too big, then you know that your model has not done well. It has not learned well to make predictions on the unseen data. Now, after assessing the loss, the algorithm embarks on model optimization. Now, after seeing your loss function, if it is high, I will proceed to the next stage, where now you optimize your model. And in this stage, you aim to minimize the error of the loss function by adjusting the initial parameters. This optimization is achieved through iterative techniques. In this case, like for example, gradient descent, maybe have stochastic gradient descent, mini batch. So we'll be going through all those in the following sessions, where the algorithm then calculates the gradient of the loss function with respect to its parameters, and then adjust these parameters in the direction that minimizes the loss. The Remember, the essence of this modeling is to minimize the loss and to have the predicted function to be as close or as approximately close to the actual function. Through these repeated iterations or processes, the model will come up to, will able to improve its predictive accuracy or ability and be able to have a better generalizability of the unseen data. So there are different methods to evaluate your accuracy, model accuracy. Maybe just short. So for classification metrics, we shall look at accuracy, precision, F1. We shall discuss this when we'll be handling classification. Then for regression, we have mean squared errors, root, mean absolute, and the R squared. So now, that's how our machine learning algorithms work. Now, what are these machine learning algorithms? So we are going to check on our 4 types of machine learning algorithms, where the first one will begin with supervised learning. So these algorithms that trained on labeled data. Labeled data means if you have an X, you also have Y. That is, if you have the predictor, you have the response variable. So it trains on the labeled data mapping inputs to output. Then for the unsupervised, this one has, you have the features, but you don't have the target variable for the response variables. In this case, that's why you have to discover the patterns with the labeled data. Then the supervised combines the semi-supervised combines both supervised and the unsupervised. Then the last one is reinforced learning. This learning where it is through trial and error, where the agent learns to make decisions by receiving feedbacks. That is reward if it performs well, or a penalty if it performs poorly from the environment, aiming to minimize the cumulative rewards over time. Now, in this case, today you are going to focus on supervised learning. So, as we had said, supervised it's trained on labeled data sets where we both have features and output. So supervised is categorized into 2, where we have regression and classification. So regression involves predicting continuous target variable. Please take note of this. Whenever you are dealing with regression, remember your output will be continuous. Continuous means takes a number, either it has decimal points, that one. Then we have algorithms that lie or fall under regression. For example, linear regression, polynomial regression, ridge, lasso, decision tree, and random forest. For classification, this is predicting categorical target variables. In this case, we have discrete categories. That is, it is either 1 or 0. That is, for example, if it is binary classification. Now, to that point, we are good. Hello, jambo. We say in Swahili jambo. Habari zenu. That is how you're doing. Like, are we together? Albert, are we okay up to that point?
Hi guys, your response is very necessary. If
All
they
right.
have issues, they probably would signify.
Thank you, please. Yeah. Now, now we are going to focus. Today we'll focus on regression because of time. So, regression, as we have said, it has so many categories of it, from linear to lasso. Now, as we said, the machine learning algorithms operate on mathematical operations. So please take note of this so that whenever we make the model, we'll be able to understand how we came up with the output. So, okay, I hope I'm not seeing mathematics here. So simple linear regression, it is a statistical method that allows us to understand and predict the relationship between two continuous variables. In this case, we have y. Y is the dependent or the response or the outcome variable, and then x. X is the dependent predictor. Yes. Now we come up with this equation where y is equals to mx plus c. You can write in different formats. So y is the response variable or the dependent variable. M is the slope of the line. There are those that use B naught to indicate the slope. Then we have C. C is the intercept. That indicates the value of y when all other variables are held constant, so they are equated to 0. So on simple linear regression, we have reasons why we should use it. Why should you use it? When you want to make predictions. So it enables the prediction of the dependent value based on the dependent. On the next one is inference. So this is now statistical. So if you want to get insights on the relationship between the two variables, or maybe if it is multivariable or multivariate, linear regression or multiple regression will be of help in this case. Now, before you do any model on linear regression, please, there are statistical assumptions that have to be met. Remember this one, this inference. So for you both to make correct inference and appropriate predictions, the following assumptions have to be met. So linearity, remember we are dealing with linear regression. So in this case, we assume there is a linear relationship between the dependent and the independent, the dependent variable and the independent. We must see that linearity. Then the next assumption is homoscedasticity. This ensures that there is constant variance on the residuals across all the levels of the predictor variance. Now, if this one is not met, then you'll not be able to make estimates of the coefficients, and you cannot draw a conclusion to ascertain that the output that you have has met the statistical requirements. Then you go to multicollinearity. So multicollinearity is a situation where there is strong correlation among two or more of the predictor variables in a data set. So in this situation, if you find maybe two or more variables have collinearity, have strong correlation between them, then that means you can drop one and then have no impact on the model. Because in this case, we say if they have strong correlation, the effect of one variable can be explained perfectly by the other variable. So please forgive me, I'm getting too much into statistics, but it's better you understand how it goes through. So the next one is independence. So errors in this case are independent of each other. Then that ensures there should be no correlation between them for reliable statistical inference. Then we also check on normality. Your data has to adhere to the Gaussian distribution. Does it have the bell shape? Then if it doesn't, then linear regression model would not be a fit for that model or for that problem that you're trying to solve. Then also check on outliers. From our data science knowledge that we have, outliers are those data points that are extremely above or below. Now, this is the equation for getting the residuals. Residuals here means the errors. Also, these are just formulas that I come up with, just in case someone may need clarification. Okay. Now, up to that point, are we okay? But now we can go to a practical one. We do practical one.
Yes, we are okay.
Are we okay with the overview of the machine learning? Please, if I am too statistical, please let me know. From statistics department, so they will
Yes, they
understand.
all gave an affirmative response, so everybody's
Uh,
okay. Everybody has
now,
given it.
thank you. Now, the next thing I would request you guys to maybe open your Google Colab or wherever place you use to do modeling or to do your machine learning task. Are we familiar with the Google Colab or Jupyter Notebooks, Kaggle, for those who participate in the Kaggle challenges or DeepNote? Are we able to have access to those IDs? Yes, please. Uh, yes, please. If you have, you can open yours so that I can share the data, the link to the data set, so that you can be doing the same thing with you. Machine learning is done by doing, so you understand it better if you do it. Are we good? So please, if your ID is open, let me share the link.
Okay, Enoch, I think you can share the link already, or Isa would be using a Jupyter notebook.
Oh, okay.
Just share the link on the chat box.
All right. So that is the absolute link to the data set that we will be checking on this. Please load it. When it's done, let me know. Yes, that's the link, please. Where you have a challenge loading the data, let me know. Can I help out? Are we good?
All right, Enoch. So we're just seeing your
Yeah, I want to share the, I want to share the screen now for.
okay. Thank you.
All right. So the data set that we are using here, in a very the underscore indicators data set. So it comprises of socioeconomic and environmental data collected from various countries, focusing on factors related to sustainable development. So the information included in the data set is as follows. We have the country, which is the name of which country that where the data was collected. We have forest coverage, the percentage of land covered by forest. So this indicates the extent of the forested areas within the total land area of each country. The biodiversity index, in this case, this indicator provides a measure of the variety and the variability of organisms within each country's ecosystem. We have protected areas. This is the land designated as protected areas. Then we have deforestation rate. This is the annual rate of deforestation that it quantifies the percentage of forested land that is lost each year due to deforestation activities. Then we have carbon sequestration, the amount of carbon dioxide that is sequestered by the forest. Then we also have soil erosion. We also have land degradation for rural population, and then population density. So the first thing we import our data. Then before importing our data, we have to now import the necessary libraries. In this case, I hope you have imported yours. So this libraries. So I'm using DeepNote as my ID. Please, I may not be using DeepNote book color. So these are the libraries. So if you want me to share the libraries on the chat, please just notify me, share. So we have imported pandas. Pandas is a library in GitLab that is used for data manipulation. Then we also have imported NumPy. NumPy is also a library that is also used for numerical calculations in data science. So we also import stats model. Another thing to note, when you are using GitLab, it's limited when it comes to statistical libraries. Yes, it has some of them, but it is not entirely encompassed with the necessary or all the statistical libraries that are needed for you to make sure that your model meets all the statistical requirements. So in such case, we import stats model. So the stats model will give us access to all the libraries that are rich in statistical analysis. So then we import matplotlib. I hope you know this. This is for visualization. Yes, now those are libraries. Can I share maybe if someone wants to run the same thing to me? Okay, let me share them. You can see on the chat. Now, please let us be doing the same thing so that when you get here, I can know. So those are the libraries for the first step. You can run them on the step. So after now running our our libraries. And just grab them again. And start with- okay. Are we the same up to that point? Now, those are your libraries. Now, when you have your libraries already in the setup or in your IB, that means whenever you run anything or you call any library that you devoted, it will work perfectly well. Now we go to read our data in this case. So you are using this method, pd.read_csv. Then you provide the absolute link. Maybe for other cases, maybe someone may have the data set downloaded. In that case, you just pass or you upload it, then you pass the path where it is located here. Then now you run. Now after running, we are running, this is the name, environmental indicators, that is the name of the data set. So after running, we run .head. .head means you want to check the first rows. In this case, you can put a number and change from 10 to 5. And put a number, it will still work well. This one is just to check the first rows of your data set. So up to that point, are we okay? So that's it. Now, yes, I can see someone has raised hand. Yes, you can speak or just type on the chat. I'll check. Now we go to the next one. So you can use different approach. For example, there are different approach now to do your EDA in this case. You can just type the environment like the data set, the data set name, this one. If you run, you'll get the same thing. So you just show what I mean. So you can just run this command. Info is to check the names of the columns, the data types. If you run it, give you let me see. Are you able to see this? The data type, the memory of which it is storage. But now that is not, people have different approaches. You can print, for this case, I printed mine. Now I'll continue with the one that you've done. So I want to check the summary statistics. This command here is to check the first rows of your data set. After that, now you want to check the summary statistics of your data set. You want to check the mean, the median, the variance, standard deviation, the kurtosis. Then you run describe, this one. Okay. Still, there are those that want to do it maybe when it is transformed, you can add a T, that case, it will still give you the same output. So when it is transformed, now this is the summary statistics of your data. You can see the count of which variable is that 2. This when the screen is just more, let me know. So this is the summary statistics. We have the count, mean, standard deviation, the minimum, that is the 25. That is the first quartile. We call it the first quartile. That is the 25%. We have the median, which is the 50. We have the third quartile, which is the upper quartile, 75%. Then we have the maximum. So whenever you're doing the EDA and you have obtained your summary statistics like this, I would like to pose a question. What can you infer from these summary statistics for those that we are together here? Sorry, I already imported data without the heading. What do you mean without the heading? Yes or yes, what do you mean by without the heading?
Okay, let's just give her a minute. I think she's probably typing a response. But Isa, you can also unmute it. You don't worry, your voice is not affecting the recording or anything. Would love to hear your beautiful voice so to make it more fast, to make the process faster.
Sorry, I'm not making it. That's why I was typing. So when you copy your data, you before you use the code, I'm the beginner to Python to like playing through it. Yeah, so when you imported and you use the code, I had one environmental, I cannot even remember exactly what it was. I was not imported data. I don't even remember. Are you getting me?
Can anyone help me and get her? I have not heard anything. There is a lot of like echo. I can't hear well.
Yes,
Please.
that's true. Or that there's a lot of echo while you were speaking, so we could not really pinpoint what you were saying.
Okay, now let me respond just to what maybe she could have said. If not, I'm not sure.
Can you see now?
Yes, it's much better. So you can go
Yeah.
ahead.
So I have to go out. I'm in an office.
And now we can't hear you.
So I could not speak. So when I imported the data, I did not use that line of code where you had I think you had the heading name, environmental something, and then you had dot head or something. I just
Oh,
like imported directly without that. That's why I was asking him that is it going to be a problem? And then,
yes.
please, sir, you are really, really fast. I think following you, except if you want us to just follow and get the line of codes and then do it practice on our own later and then probably submit our notebooks to you. Because if we are to follow you as you are doing it, you are actually very, very fast. Thank you.
Apologies for that. Thank you. Apologies. Sorry.
No, no
I think
problem.
I think
Thank
I'm
you.
very fast. No. Okay. Yes. I want to answer your first question. The name that you are seeing here. Okay. I've already let me share the chat. Oh, I've already sent you the chat. So the name that you are seeing here, this one, we call it in programming a variable. A variable is used to store either data or content, or it's like a container that stores your content. So if you just import it directly without storing it anywhere, so when we get to deeper analysis, you'll be having some challenges to pass the variable or to pass the whole string of it to the function that we may be creating. So this one is a variable. You can give it any name that you want. You can say that df. You can give a name of your choice. So please, it's good to have variables that stores the content or the data that you're doing in this case. So you can give it any name, not necessarily an environmental indicators, a name of your choice. Then the next line of code, after you have given the name of your choice, you put that name or that variable name dot head. Then you put the parentheses. In this case, dot head is a function that displays the first rows of any number. If you don't put a number inside the parentheses, initially it is always the first 5, but you can put a number that you want. So if you run that function, it will display the rows, either the first 5 or according to the number that you have inputted, it will display the rows of those what of that data set. So please let everyone run that one. I would like so that we do it the same thing, because when it gets to the statistical part of it, you know, you need to have it on your side. Please run this one. All right. The next one, I'll be sharing the codes that we run it together. I've said you can run this if you want to get the deeper insights from the data. That is, if you want to know the data types, the count, if there are any missing, you can run this one. That function info.info will give you all those details. Now let me give you the next one that I explained and also run it on your site. I think that one can help. So run those consecutive commands that I've tested on the chat. Guys, let us run those commands, those commands, please. I will continue to explain as they run it on their side. My guys here are not speaking. I don't know if they have their collab or whatever I did, they're using open. Please put someone. We have invent insurance agents. Are you on the same page? We have Ibrahim. Hello, Ibrahim. Are you running the codes as we are doing on this side? So we also have Ojo. Hi, Ojo. Please confirm if we are together, or if you are left behind, please just raise the alarm. The better you go slowly, but you understand step by step. Right.
Oh, Ibrahim has given a response. He's following.
Okay, good. Now let's continue. Now I've said people may use different formats. Now this is my format. You can still run this one without any print function, and it will still give you the output. So describe, I'll be maybe going through the function. I've handled the add. Describe is the one that gives you the summary statistics. This here means you transpose it. Transpose means changing columns, they become rows, and rows become columns. Now that's the function of the key in that case. The next function is null.sum. So null is going to check, do we have any null values in the data set? Then the sum is to put or to group those missing values together and then give you the final count of them. Now that's the function of those. Now that is what those two do. Now there is another function here. I want to go ahead now. I want to exclude numerical columns before computing correlation matrix. We are just ending there, so no problem. So I had a question here. My guys, this is where machine learning meets statistics. Now, when you find we have this type of this is the main standard deviation. So
Okay, sorry guys. I think that must be Enoch's network. Would join us back soon. All this extra work that be giving somebody stress. So sorry. Enoch will be joining us soon.
Hey, sorry guys, my network dropped.
I have no problem at all. There, you're back.
Yeah, okay, now let me respond to this. So the question I was asking, so if you find there is a big deviation between the mean standard deviation and the upper quartile and the lower quartile. Now this tells you that as you go to fine tune variables and the dependent. To do this, first of all, you create a correlation matrix. So for you to come up with a correlation matrix in a Skitlan, you can use different formulas, but I used this one. There is this function when you call just the name of your variable, then dot call and parentheses that prompts skitlan library to give you the correlation matrix. Now, after printing your correlation matrix, now this is how they appear. In this case, I can see there are so many, like, can see this diagonal one. Wherever you see one, that means it is that variable versus itself. Now, in this case, we go the next one. We want to come up with a correlation map. We are finding that this one may be difficult for those who are not familiar with statistical part of it, that they can interpret or just check. Like for this one, like for these ones. So we go the next one. We come up with our correlation int map. So okay, sorry, I forgot to give you this code here. When you run the same code. That is it. That is the code for the correlation matrix. The next one. Now, just maybe if you have may have question on the correlation matrix. So in this case, you are trying to check, do we have the correlation coefficients, they lie between -1 and 1, where the far the value is from the 0, either towards the negative or towards the positive 1, the stronger the correlation. So that's how you can interpret them, maybe if you are not maybe familiar with it. For example, this one is closer to 0 than this one, right? So those have different correlation. The strength of their correlation is very different. So the negative ones means they are negatively correlated. The positive ones means they are positively correlated. Now, these correlation values, they are useful when you are doing feature engineering or feature selection, where we shall drop some variables here based on the correlation coefficient. If it does not have any strong correlation coefficient with the dependent variable, then it means it has little impact on the dependent variable. So that means you can eliminate it, and still you have your model performing at the highest level. Now this is the code for plotting the heat map. That is the next code. Please, wherever it is not maybe running, please let me know. So that is correlation heat map. So remember correlation heat map and pairwise scatter plots are used to check multicollinearity, and the multicollinearity is one of the assumptions that we have to satisfy. Now, this is the output for the diagram of the correlation heat map. So based on this heat map, what can we see? What can we infer? There is some correlation between the variables. Deforestation and forest coverage, you can see it here, even on this one. Let me take you this one. Can you see it? So can you see forest, where I'm pointing my cursor? Yes. Then deforestation. So when you come to deforestation, you find 0.56. Then when you go to, that is on the forest coverage side. When you go to deforestation, you find the same value. So those two are correlated. But you guys, maybe you have different interpretations. So it all depends. That it is not fixed that you use mine. Maybe you have a better one. But there is also a one that will always come out with the diagonal matrix that can help you. So I did not handle that one here because it takes some coding. So there is also a correlation between soil erosion and forested areas, soil erosion and carbon sequestration, land degradation, and carbon sequestration. Those are all correlated. Now, knowing that the relation between the variables, now it is our time to start building our model. Okay.
Excuse me.
Yes.
Last code for me is giving value error. This one to draw the heat map.
The heat map. How?
Yes, I copied it just like
the way
I posted in the chat. Yes.
Okay, let me try it again. Let me repost it. So make sure you run the codes above because they are all dependent on each other. Make sure you also run this, which one? This one. This code here. This one. And also this one. Make sure you are from the first one to where we are. Make sure you have run all those.
Yes.
It's okay now?
No, it's still giving error.
What type of error?
It says value error.
Value error.
Yes.
Mm-hmm.
It's flagging the line 4, the one that says core matrix equals numeric dependent variables dot core.
Okay, let me check it. Line 4, this one.
That number 4, that line 4, yes.
Oh, okay. So have you run this one? Because the correlation matrix, it is a variable that is holding this one. This here. Because it's running on my side, I'm wondering what you may have omitted. Okay, now let's continue to look into it. Then maybe we'll share the error code. Okay, then I check it on my side. Maybe something is missing. We don't know. Now we want to now try our model. Now the independent variables, these are the code in the independent columns. We have forest coverage, forested areas. These are our independent variables. Then the dependent variable is the biodiversity. We want to come up with a model and check, does it meet all the statistical assumptions before we proceed with anything else? So remember, there is something that I showed you, y is equals to mx plus c, right? Remember that one? We remember that formula for linear regression, that y is equals to maybe beta naught, beta 1, x1, that way. Do you remember that? Now it's coming to play in this case. As we categorize our independent and the dependent variable, this one, this one. I've tested that one for those who are running the code. So it's coming to play in this case. The formula string in this case is a y is equals to the formula string that I want to come up with. It is the dependent variable. This case is the biodiversity. Then plus, now this one is the, what do you call it? What do you call it in programming language? Tilde, yes. So this one is tilde, that like y is equals to, that is the stands for that. So this is the tilde. Then plus, then this plus, we put it in the quotation because it's a string. Then plus, you join the independent columns. Now you produce the formula string. You want to display it. After displaying it now, remember what we imported in our libraries, SMF. SMF is the formula now that we imported from the stats model that is used for OLS. OLS means ordinary least square regression model. Then we fit our model, then we print the summary. Now, this is the output. If we print our regression, our regression results are as follows. The model is OLS. We have the R squared value, which is 0.967. Then adjusted R. The R squared, it is a test for goodness of fit. It tests if your model has learned well on the data sets that it has trained, the goodness of fit. Then we go to the next one, we go to intercept. So this is the intercept. We have the correlation coefficients. We have the p-value, this case. Now this is statistical part of it. Now from these values, we shall see where we shall employ them. From these values, it is where we will come during the feature selection part. You will come to drop variables that have less correlation with the dependent variable, or whose p-values, this case here, p-values are either greater or less than the dynamic or the typical threshold p-value. Now, after running this code, we run it, test it. Don't know if they tested this one. I know you're wondering, why are we not just going to predict, then model evaluate? Now, please, before we get to that point, that part is easy. Understand. This is where statistics meets data science. You find we as young data scientists that are coming up, we only train the model evaluate, but we don't assess the quality of our model. Amongst your independent variables in the data set. So what do you do to handle multicollinearity? As we said, we shall drop the features that are highly correlated with each other. And also, before you drop, now this is where feature selection or variable selection comes in. Variable selection entails different methods. I will discuss the other three on another day, but I will point out the one that we'll use in this case. You can select variables via correlation and significance. Are the variables that you are picking significant, or do they have strong correlation? Or you can select them by either variance threshold. In this case, you are going to use the first one, correlation and significance. Guys, my network is just dropping me out. Okay, after apologies. Please bear with me. Let me finish just on this part, then we shall continue. Okay, good. So can you see the screen?
Yes.
Yeah, so we were saying where we use the p-values. The p-values we said are the ones that we use to reject or fail to reject the null hypothesis. Now, if our p-value is less or equal to the one that we choose, we say we reject the null hypothesis and say that they are statistically significant. If not, we fail to reject and conclude that they are not statistically significant. So I was saying that is the reason I dropped this. So please, as you run on your side, check on that table. You will see why we dropped these ones. Now we want to do our model again now using our fewer variables than we had. We want to see if you can maybe silence the multicollinearity issue that we had faced above. Now this is the next code. Let me copy it. That is the next code. So if you run our code now, we'll come up with the next results. Okay, that is the second code. Now, if you run up with, we want to see if after dropping those variables that are highly correlated and add lower coefficient values with less or that were not linearity. Yes. Now, what is the difference? I want you to see here. The first model had this one. Let me go back. The first model had this value of r squared, 0.967, and just add r squared, 0.956, right? That is after we included all the variables. Now, after dropping the less of our r has remained, it has retained. So r squared is still 0.966, 0.59, 0.959. So what does that imply? Implies that the variables that we have dropped had little impact on the model. So we could have trained our model without them and still get a better output because the variables that remained are able to explain those that have not been captured well. So we have handled our what? Multicollinearity. Now we go to the next one. We want to check, that is the first rule, the first condition of the first assumption has been satisfied. We want to check collinearity. We want to inspect, is there a linear correlation? Is there a linear relationship between the dependent or the predictor and the response variable? Now to do that, we plot scatter plot. Now this is the code for scatter plots. That is the code for scatter plot. Please run it on your side. Now, after plotting our scatter plot, you can see we are plotting a scatter plot of the dependent variable versus the independent. In the first case, we have forest coverage versus biodiversity. Biodiversity is our dependent. Forest coverage is independent. You can see here. How many variables here have linear relationship? Like for the first forest coverage, there is no linear relationship. If we draw a straight line, it does not visually display relationship. Protected areas versus biodiversity. Still, there is no pronounced linear relationship. However, when you check on forest deforestation rate versus the biodiversity index, we can see if you are to draw a straight line. Remember, linear regression is about fitting the best line of fit. If you are to draw a straight line, the points will lie closer to that line on deforestation rate versus biodiversity than the other variables. So we conclude that only one variable shows what? Relatively linear relationship with biodiversity, which is what? Deforestation rate. Now I want to check on another thing. Here's the next code. Don't leave it there. Yeah, as they say, the following is very fast. Maybe you are going very fast. Now I want to plot. We want to check now the next thing. Is there a relationship between the predictor variables and the model residuals? Do we have any relationship to assess? The next condition that we are assessing or assumption is the independence. Remember we said independence is there the residuals of the predictor variables remains constant across all the levels of the predictor variables in the data set. So how do we identify so? We do so by plotting scatter plots still. The residuals, the scatter plot of the residuals versus the predictor variable. So this is the code. Oh, something is being cut off. Please check if the code is not full. Please let me know. Sometimes these codes they refuse to be pasted. Okay. See, this one is cutting something off. Let's this part from this part. I want to see very fast so that we finish before we go. I will go the next one. Now, after plotting our predictor variables versus the model residuals, we want to check, is there independence? Our residuals or the errors of the model not correlated. Do they depend on each other? We want to see that they are independent. Now, by plotting this, you can see from the red line, the red line is moves from the 0 all the way across. So essentially, for us to ensure that there is independence, the residuals are approximately uniformly and randomly distributed about the 0 axis. In this case, you can see they are random, yes. Are they uniformly distributed? Yes. Still, you can see clear pattern of uniform distribution across or along the 0 x-axis. Another one, we need to ensure that they are not forming any specific groupings or clusters. So you can conclude that yes, the residuals are present, yes, but you can see any groupings or patterns, suggesting that our errors are independent. Values. Now let's check. To do that, there is a statistical test that is employed. We call it Rich-Pagan test in statistics. So this test is the one that you are going to use. It is that statistical test that confirms the presence of heteroscedasticity. Heteroscedasticity means the variance is not constant of the errors. So you want to confirm. So to Now, when we do this test, we focus on the p-values. It is the p-values that gives us an answer or gives us conclusion to infer that we don't have heteroscedasticity or to conclude that homoscedasticity has been satisfied. Now let me paste that code for homoscedasticity. Please don't get tired. It is becoming too statistical. sorry. Machine learning is more of statistics. Actually, almost 75% maths. Now, if you run that code, no, these are the results of the Rich-Pagan test. So how do you interpret these ones? We are focusing on the p-values. Remember, we have said the p-value. These one, we are going to focus on those two. The p-values of both LM test and F test are larger than the typical significance level of 0.05. This indicates that there is not enough evidence to reject the null hypothesis of homoscedasticity. What does that mean? If they are greater than 0.05, then homoscedasticity has been met. That means there is no heteroscedasticity. Or in short, that means the variance of the errors is constant across all values of the predictor variables. Now that means we can continue now with our data. We go to check almost the second last one, which is normality. Now, what is the normality of our residuals? How do we check it? We check it by doing two things. We can plot an histogram or a QQ plot. QQ plot means quantile plot of the normalized residuals. So this is the code for checking normality. Somebody may ask, why do we need to check for normality? We need to ensure that our data follows Gaussian distribution or the bell shape, so that when you are maybe, how do you put it? When you are giving inferences, you can know the statistical test to apply. Some cases, when we get to classification, we'll be doing chi-square tests. Now, chi-square tests, those are tests that lie under parametric test. Parametric test means the data has to follow normal distribution. Now that is what we are checking here. So if you run the code, the QQ plot of the normalized residuals is as shown here. Now these points, for you to know that it follows Gaussian distribution or the normal distribution, the points have to lie close to the red line, the diagonal line. They have to lie close to that line. Now, if they are scattered or they lie far from that line, then you know your data is skewed. It does not follow normal distribution. And the next one, the last check that you check is to check for the outliers. Now we talked about outliers. Outliers, we said they are those values that are extreme, either far away or far below. That they are too big or too small from the rest of the values. Now that is the code for checking outliers. Now for you to check or to be able to detect outliers, you use Cook's distance. Now Cook's distance is a measure used in regression analysis to assess the influence of individual data points in the regression model. You want to check, are there individual data points that have a huge impact on the model if they are removed? When you remove those values, does your model generability get poor, or don't they have maybe, or do they have little impact that you can do away with them? That's why in data imputation, you are told before you do away with outliers, please investigate. Do they have an impact on the regression model? Now, for you to do that, you must check the Cook's distance. Now, these are the Cook's plot distance check look like. You can see from these points that we have a point that's too above, let's say very far, just closer to the upper edge of the plot. Like we have how many points? One, we have 1, 2, 3. Like we have a few points that indicates that outliers. Now, what do you do? How do you conclude on Cook's distance? So a rule of thumb for determining whether Cook's distance is too large is whether it exceeds 1 or greater than or equal to the value of value of 4 divided by the number of the observation. So before you come up with your final answer, you check, like, does it exceed 1? Okay, if it doesn't, is it greater than or equal to the value of 4? That is 4 divided by the number of the observation in the data set. In our scenario here, none of the distances exceeds 1. And when divided by 4, when we calculate 4 divided by the number of observations, which are that 2, in this case, you can confirm this one. So 4 divided by that 2, you get 0.125. So what do you conclude in this case? There are 3 points that we have seen that may demand more examination and may influence our model. So values that is 0.23, these are the individual values that are larger than the others. So ideally, we can train for you to check if these 3 values, the values that we identified with the outliers, if you want to check their impact on the model, you can train by you can train the model with 1, eliminate 2, or eliminate all of them and check the performance of the model. Now, that's about the statistical part of it. So I wanted you to understand up to that point that next, we'll just be doing modeling, evaluating, getting the R value, getting the root mean squares, then prediction on the unseen data set. Are we together up to that point? Or have become so statistical? Sorry. Okay, can you maybe get some point of views from your side? Remember, I'm amongst you, just appear. I'm not an expert. So yes, please say something. Guys, are we together or I'm talking alone?
We are together.
Yeah, please say something. Up to that point. Please, I wanted to introduce that part first because I would not like I would not like to be just taking you through modeling, the normal way you usually do it, without understanding the statistical background of whatever you are doing. Because remember, for you as a data scientist or a machine learning engineer, you give inference, and your inference has to be supported by statistical evidence. Now, this is where you get your statistical evidence that you can be sure that you can say I'm 95% confident that the results of the model that I've given, if subjected to any other test, they meet all statistical tests and they can withstand the test of time. So please, that's why I opted to take you through the statistical part of it first, so that you understand before we get to modeling. The other stuffs are just easy, but I will be taking you into deeper part of it. There is someone who have not said yes something. Ojo, hey, let me hear from Ojo. Ojo, say something.
I'm having some trouble on my side, so I'll just follow along for now. Then hopefully I can get this recording so I can go back and revisit all of this in my spare time.
Okay, good. Just in case you need the codes or the notebook that I've been using, please don't hesitate to inbox Joy and share so that we all have strong understanding of the statistical part of it, please. Any other comment? I think I would not want to continue from. I want to continue from there. I would like to stop here. Any other question? Yes? So, okay, let me stop sharing this. Yes, please, let's say something. We are all here learning. Also, I can also learn from your side, you guys from your side.
Okay, I don't think they have a question. Or Isa only mentioned that she's thanking you, and she says it's quite a lot for beginners. Well, you did a very good job explaining that she's going to go back to sit with it. She's saying thank you once again.
Okay, thank you. Okay, guys, we have only handled the regression. The next time we shall be doing some now projects from the start to the last. And now before we get there, I will be just be going step by step. We have handled linear regression. We have understood the background behind linear regression and what is so about linear regression. Polynomial regression, it just deals on linear regressions. This means these are values that are not, they are taking more like it is maybe x squared. That is what they mean. We also have ridge regression, lasso regression. So we shall maybe take some days discussing on regression and classification because 75%, like 75% to 80% of all predictions or of all machine learning models, they base on these two. And if you're able to understand, please make sure you understand regression very well so that when you get to deep learning, it will become more of maths. And I would like maybe you to be able to understand, to build from this one, that what we have been doing. If you need the mathematical part of it, please hit me up. I'll give you mathematical how you can get the same results. So I want to say thank you for having you guys. It was my first time. I have not disappointed you guys. Thank you so much. Thank you guys.
Thank you so much, Enoch.
Thank you, sir.
Thank you so much. Thanks so much for providing more clarity. And yes, thank you all for joining as well. I think next time we join, people can probably also come up with questions so it can be more specific as to the direction it would take to addressing you people. All right. So thank you very much, everybody, for joining. Do enjoy the rest of your day. Thank you so much. I'm looking forward to having more sessions with you. Thank you. Thank you, guys.
Thank
Bye.
you. Bye.
Oh,
Thank you too.
Oiza has something to say.
Okay.
Oiza, you want to say something? Okay, I think she just raised her hand by mistake.
Yeah, it was a mistake.
So,
Sorry. Thank you very much.
right. All right, no problem. And you guys can also make use of the group chat if you have any concerns or you have probably any problem you're encountering as you navigate the data camp platform. You can just do well to drop your message on the group chat. Don't worry, we have a number of people to reply and provide more clarity, right? And that can also inform what steps to take or what we should focus on in the next peer tutor session. So I hope that's fine. I know. All right. Thank you very much, everyone. Thank you, Enoch. Thank you once again. And do enjoy the rest of the day.
Okay. Thank you. Bye.